Hello everyone. We're going to continue our look at integrals with some general rules, and maybe we'll get some actual integration later. So let's go ahead and see what we got here for today. Tyrannosaurus T1111RT, known as Rexy, is without a doubt one of the most recognizable dinosaurs in Jurassic Park. It's the very first Tyrannosaurus Rex, who goes all the way throughout the movies, all the way in through Jurassic World you see him. It's the one with the 3 claw marks on its neck. That's Rexy. A typical velocity curve for Rexy accelerating from standstill is given by this function RVRT, and that's a lot, so I'm not going to bother reading it all. But using this velocity equation, what is Rexy's average velocity from 0 to 8 seconds? So this is a new kind of question because it's asking for an average velocity, not just for velocity. Now, to start things off in this section, or the second day of the section anyways, we're going to look at some integral rules, and I'll try to show you the main features of them. So this first one is the zero rule. And this says that if you integrate from any number to the same number, in this case we have a to a, but let's say the lower limit was 2 and the upper limit was 2, that integral is going to be 0. Now, like all of the properties here, that should make sense when you think of area as area, or integrals as area, because if you go from a to a, there is no area there, it's just one straight line. So no area there means that the integral should evaluate to be 0. This next one here is additivity, and to do additivity, let's say we start our integral at a and then we end it at b. To that, we add another integral of the same function that starts at b and ends at c. So you notice how the upper limit of the first integral matches with the lower limit of the second integral. Well, if you put that all together, you should just get the integral from a to c of the same function. And that kind of makes sense because you find the first area from here to here, and then you find the second area from here to here, add them together, and you get the area from here to here. So that's how the additivity works. Number 3 is the order of integration. This is a favorite for a lot of simplification purposes, but if you take the limits of integration and you reverse them, what you create is a negative of the previous integral. So you'll see in that first integral in number 3, we go from the blue to from the yellow to the blue, and that's the same thing as negative of the integral from blue to yellow. So they work as negatives if you reverse the upper and lower limits. Next, if you integrate the multiple of a function, so k times f of x, that's the same thing as multiplying k times the integral of f of x. So a constant can be multiplied in the integral, or it can be factored and brought outside the integral. Either way you do that, you get the same value. And this is nice because if you know the integral, for example, of cosine, then you can find the integral of 10 times cosine just by multiplying the result by 10. And the second part here is basically the same thing, but using -1. And that's handy to know also. Moving over to the second part of this, we have sum and difference. And this should kind of make sense. If you add the integral of, if you say you integrate f plus g, then that's the same thing as the integral of f plus the integral of g. And if you do integrate f minus g, then that's the same thing as the integral of f minus the integral of g. So let's say we know how to find the integral of x, and we know how to find the integral of cosine. Then if I want to find the integral of x plus cosine, then I just need to add those two integrals, take those two integrals separately, and add them together. 6 and 7 are kind of nebulous. And I think for 6 and 7, we'll go take a look at a graph of an f of x. For 6 in particular, take a look at what is b minus a. That is just the width of the integral. So if I'm integrating from a to b, b minus a is the width of that integral. So let's take a look at a graph of this then. The first thing to look at is the integral of f of x from -2 to 4. And I'm just going to pick -2 to 4 as my a and my b here. Now that's going to be this yellow area over here. The next piece of the inequality, the max-min inequality, is this minimum value of f multiplied by b minus a. Now if I create another graph, this is the exact same scale of the previous one, and I say, hey, what is the minimum value of f? That's going to be right here. F doesn't get smaller than that. B minus a is the width of this rectangle from -4 to 2. So if I multiply this by the minimum, what I'm essentially doing is creating a rectangular area of this. So this blue here, this blue area here is the same value as a minimum of f of x multiplied by b minus a. And as we can see, the minimum value of b minus a, or the minimum value of f multiplied by b minus a, that has to be smaller than the integral from a to b. Now the third part of the inequality is the maximum value of f multiplied by b minus a. Now I know what the b minus a is. That's the width of the rectangle. But with the maximum value of f, that would be at the highest point, which is right over here. So if I draw a rectangle where the height is the highest point in that function, and the width is 4 minus -2, I've basically created an area which is as big as possible. We would say that this circumscribes the function. So if we take a look at the three areas together then, we can definitely say that the minimum of f of x multiplied by b minus a is less than or equal to the integral of f of x from a to b. And that in turn has to be smaller than the maximum value of f of x multiplied by b minus a. I think graphically this should make a lot more sense. This last one here is domination. And in domination, if one function is bigger than the other, then the integral of the bigger function has to be greater than the integral of the smaller function. For this next one, domination, let's take a look at the two functions graphically, and we can see that the purple function is always greater than the green function. And if I compare the area under each of those curves separately, I can tell clearly that the area under the bigger function has to be bigger than the area under the smaller function. And that's all that domination says. It says that the area under the bigger function is always bigger than the area under the smaller function. So with an understanding of how sum or min-max and domination and all of the other functions work, or all the other properties work, let's take a look at this problem here where it says, suppose we know the integral from -1 to 4 is 3, and we know the integral from 4 to 1 is 2. Can we find the integral from -1 to 1? Well, look at this. The upper limit here matches with the lower limit of f over there. Also, we have a correspondence with this -1 over here and this 1 over here. So visually, if you line those up, this is the same as sum and difference, or as additivity, I should say. When we line them up and add them, we can see again how these Integrals work together under additivity. Doing some substitution in basic maths gives us that 3 plus 2 is 5. And then putting it all together, it's pretty easy to see that f of the integral from -1 to 1 of f of x is 5. All of that can lead us directly to one of the most tested concepts on the AP test, which is the mean value theorem, or the average value theorem. You've probably already seen an average value theorem, but this is in particular just the average value of a function. That's the way I like to think about it. So let's remember how to find the average of something, a set of numbers, in arithmetic. In arithmetic, we just add our set of numbers together and divide it by how many numbers there are. So 1 over n multiplied by the sum of x1 to xn. With our new knowledge of mathematics, our new notation, we can look at this as 1 over n multiplied by the sum of xk's. Now this sum of xk's and the 1 over n, that kind of directly translates into an integral. Integral is just adding a function together. So if we add a function together, and we divide by b minus a, we create the average value of a function. The average value of the function, and you really can't get anywhere on the AP test without seeing the average value of a function. So really, this is something that you have to memorize. The average value, the average of anything, and I'll say this, and I mean this, the average of anything in calculus is 1 over b minus a multiplied by the integral. So if I want to find average velocity, I do 1 over b minus a multiplied by the integral of velocity. Okay? And based on domination, we can say that the average is got to be bigger than the minimum of f, and it's got to be smaller than the maximum of f. Which kind of makes sense. I mean, if my average speed on a drive to San Diego is, 62 miles an hour, then, my average speed, that 62 miles an hour, that has to be somewhere bigger than my least speed on the freeway, I guess. And it has to be also smaller than my maximum speed. There's no way the average is bigger than your maximum speed, right? There's no way the average is smaller than your minimum speed. So the average is kind of a middle number between the minimum and the maximum, although it may not necessarily be exactly in the middle. And that concept kind of leads us into what we call the mean value theorem. Okay. Before we just found the average or the mean, now we're going to take the average or the mean and make a theorem out of it. So the theorem just says that a function has to equal its average somewhere on the interval that we're averaging. That makes sense, right? I mean, if my average speed to San Diego is 62 miles an hour, then someplace on my drive, maybe once, no, probably twice, somewhere on my drive, I have to have been driving 62 miles an hour. That's all it's saying. The average has to equal the function someplace on the interval. So that said, we can go into this problem with Rexy, and it says, what is Rexy's average velocity? All right. The average is always equal in calculus to 1 over b minus a of f of x. Now we're going to substitute things. We know that a is 0 over here. A is 0. We know b is 8. And we know my function is VRT, which is this lovely looking function over here. So we can just substitute all of that in to the average formula, which gives us this integral. And then we're going to substitute in the function for VR. And that creates a pretty intimidating looking function. But we're going to go and we're going to integrate that on our calculator because that's all we have right now. We can't find the area for this function. We don't know how to do it yet. So let's grab a calculator. We're going to summon the function, or the integral. Actually, before the integral, we need to put 1/8. In fact, I'm going to be kind of cheeky here, and I'm just going to do 1 over 8 minus 0. And I'll go from 0 to 8. Nothing wrong with that. And then we'll put in our function for Rexy's velocity. Now notice that I'm not using t, I'm just using x. That's one of the things that you're going to have to get used to on your calculator. Even though you're writing a t, it's often easier just to put x because the x button is right here, just south of mode. It's the easiest button to find on the calculator. And lastly, we'll put a dx here. And that should give me my average velocity, 14.38317. The next part of this says, based on the graph of VR, does this make sense? Okay, so we're going to graph VR right now. Here's our graph for Rexy's velocity. And when I look at his velocity on 0 to 8, I can see that his maximum velocity is over here, which is what, 24 or something like that? Maybe, yeah, 24. And his minimum velocity is near 0. His average velocity is 11, and that looks like right around here he's going to reach his average velocity. And so this average velocity makes sense because it is somewhere between the minimum and the maximum velocity, somewhere near the middle of the minimum and maximum velocity. All of this leads us to, of course, the important ideas for today. Now, of course, the integral properties that we saw on page 1, those need to be learned. Also, we needed to know what was the definition of the average of a function. And then we also needed to know the mean value theorem. Now, as far as I'm concerned, you won't have another day with this much incredibly important information from the AP test in it in quite a while. So, this was a very important day for you and getting ready for the AP test. So with all of that, let's take a look at this, check your understanding. We've got Gallimimus 1030 MF runs with a velocity curve given by Vm. And part A, what is the average velocity from 1 to 6? And part B, we're going to use the graphing utilities solver function to find out when the Gallimimus first reaches its average velocity. So this is a lot of calculator work. Let's write down the integral first for part A. So the average of anything is the integral, or 1 over b minus a multiplied by the integral from a to b of f of x, which makes average velocity 1 over b minus a times the integral of velocity. Substituting the velocity function, and we get the integral from, 1 over 6 minus 1, integral from 1 to 6 of the velocity function. Grab your calculator and put the function into the integral, and you get 28.444. And you write down average velocity is 28.444 feet per second. Now, as far as the units go, the average velocity is always going to have the same units as the velocity. Just to kind of go a little nerdy on you, the integral is going to be in terms of feet. As we learned before, if we integrate feet per second, then the result will be feet. 1 over 6 minus 1, that's going to be 1 over a unit in seconds. So 1 over 5 seconds. So when I say feet multiplied by 1 over second, that gives me feet over second, or feet per second. So the units kind of work out here just through that, the integration and dividing by a time differential. Back to the calculator, we want to use the solver to find out when the function first equals its average velocity. So let's go to the solver. Math. I like to push the up arrow, and that usually gets me to solver really quick. We'll put the left side of the equal sign, which is the velocity function, into E1. And then in E2, we're going to put in the average velocity, which was 28.444. Scroll down, and here is the way the solver works. I think we've used solver in this video series before, but I'm going to remind you that it's only going to find the value of x that is closest to whatever number I put in here. So right now the computer is asking me for a guess. I'm going to guess a number that's close to the left side of the interval because I want to find the first time this happens. In fact, I could probably put in the far left of the interval, which was 1. And the solver will find the first place, the closest to 1, that makes this equality true. To make your calculator solve for you, you need to push alpha and then enter. So it looks like at 3113. And then on your paper, you're writing the velocity equals 28.444 when t equals 3.113. So that's it. I promised you integrals, and I did deliver integrals, but more importantly, I delivered to you the average value and the mean value theorem, which are going to be very, very precious to you once you get to the AP test. So, see you guys next time. Enjoy your calculus.